A radioisotope commonly used in detection of breast cancer is technetium. This radionuclide is attached to a chemical that upon injection accumulates at cancer sites. The isotope's radiation is then detected and the site located using gamma cameras or other tomographic devices. Technetium decays radioactively in accordance with this equation dy over dt is equal to negative ky, where k is 0.1155. Okay, so before going on, let's solve this equation because this is the key equation here. Y is the amount at time t, and t is the time, and k is 0.1155. So dy over dt would be equal to negative 0.1155 y. So from here, we can do separation of variables. We can do dy by y is equal to negative 0.1155 dt. And then we integrate both sides, so we get ln y. And again, this should be absolute y, but I'm just being sloppy here. So this would be negative 0.1155 t plus c. And then when you solve for y, you will get y is equal to e power the right hand side. Y is equal to e power, and the reason I was sloppy here and didn't write the absolute around the y was because in this problem y is the amount of that substance at time t, and of course that cannot be negatives. So e raised to power negative 0.1155 t plus c. And now this can be simplified a little bit. It would help if you break it up. So into e to the point e to the negative 0.1155 t, and then times e to the c. Now, e to the c is also a constant, so e to the c can be written as another constant, let's say capital C. So instead of e to the c, we just write a big C, and we can write it on this side. Okay. And now the advantage of writing it in this way is because of what we have to find in the problem. C is a special thing in this kind of situation. At t is equal to 0, so let's first write down what these things mean. Note that y is the amount of the substance. What was its name? So amount of technetium at time t. So that means, so at t is equal to 0, y is equal to y at 0. So y at 0 denotes the amount at time 0. And so when you substitute that, the equation becomes okay, so y will be y0. And c is just c, and this is e power 0. So this is times 0. So e power 0 is 1. So actually from here we get the constant. So we get and that's important in what we have to find in this problem, as you will see. So this part is gone, and c is y0. So therefore this equation now becomes c will be replaced by y at 0. And so you could also write this one as y at time t. In fact, that's what we could have written all along, but it's okay if you just write it in the end. So this is the key equation here, that the amount of technetium at time t equals the amount of technetium at time 0 when it's just produced, times e power negative 0.1155 t. And now let's go on further with the problem. The short life of technetium has the advantage that its radioactivity does not endanger the patient. A disadvantage is that the isotope must be manufactured in a cyclotron. Since hospitals are not equipped with cyclotrons, doses of technetium have to be ordered in advance from medical suppliers. Suppose a dosage of 16 millicuries millicuries of technetium is to be administered to the patient. Estimate the delivery time. Estimate the delivery time from production at the manufacturer to arrival at the hospital treatment room to be 16 hours. Okay. So, and calculate the amount of radionuclide that the hospital must order to be able to administer the proper dosage. Okay. So 16 millicuries have to be given to the patient. However, since there will be 16-hour time lag between the production, the production and the delivery at the appropriate spot. So we have to take into account that this is going to decay during this 16 hours. So if you need 16 millicuries, you have to order a larger quantity so that that larger quantity after the decay, eventually you do get the 16. So what you need is at time 16, you need 16. So basically you have to know what should have been produced at time 0. And if we go back to the problem, 16 MCI. So at T is equal to 16 hours, we need Y is equal to 16 MCI. So therefore, in this equation, Y of T will be 16. Y of T, Y at time T is 16. at time 16. So time is also 16. And y of 0 has to be calculated. Y of 0 is the initial amount that you will order. So because the cyclotron that produces, that company has to be told that, okay, we need this much by your production. And that's the amount that the machine produces at time 0. And let's see how much we will need so that we get 16 after 16 hours. So this one can be simplified. So y0 from here is equal to 16 divided by, or you could do 16 e to the positive of this. Because when you divide by e to the negative something, it becomes e to the positive, the same thing. So it'd be 16e 0.1155 into 16. So let's calculate that. Negative 0.1155 into 16. Not negative, but positive. 0.1155 into 16. Okay, so I get 101.55. It means if you order 101.55, then by the time it gets to the hospital, it will be reduced to 16, and that's what you exactly need. 101.55. Very nice practical problem. Okay.